Today we're looking at electronics, a practical application of the principle of electricity that we've been studying. Pause whenever you need to write notes. The first electronic device we want to look at is one that we have used back in our first lab. The resistor. The resistor is a small cylindrical device with colored stripes on it. It is made by wrapping wire around a ceramic core and coating it with an insulator. But we've discussed in the past that resistance is a very bad thing. Unavoidable, but bad. Why would we want to purposely introduce it into a device? Remember, from Ohm's law, resistance can affect current flow and will cause voltage drops. So resistors are used to control current flow and to cause current drops. Let's see if we can find any on our circuit board. Well, there's one right here. Here's one. There's two together back over on this side. There's one. Can you find any more? There's one here. Any more? Oh, look, there's two over here. Did you see those? The next component we want to look at is also one that we've examined in the lab, and that's a capacitor. Remember, the capacitors has two conductors separated by an insulator. So they are flat, like the three over on the left, and they can also be little cylindrical cones, like the two on the right. And the cans, they're rolled up in order to conserve space. So as shown in this diagram, there are two conductors. Each plate is connected to a different side of the battery or power supply and draws opposite charges. Remember, opposites attract, so the pluses and the minus want to get together, but they can't because they're separated by this insulator called a dielectric. Charges can't get to each other, and they keep building up and building up and building up until we're ready to use them. They're large charge that they're building up, and that's their purpose. They're used to store charge. This is capacitor's purpose, used to store charge for later use. Let's see if we can find any of those on our diagram. Well, here's one of the flat ones, and there's one over here, and there's two peeking up way in the back. Can you find any more? Oh yeah, here's two more blue ones. There's a little orange one right there. Yeah, there's, you guys see, oh look, here's one. Here's another little flat one. Orangish over here. And then we got a bunch of those cans. There's one here. There's one here. They're all over the place. Look, there's there. Did you think we needed to build up all this charge for different reasons? For some reason, they needed to store charge and just use it once in a while. Here's another one. Here's a big one right there. Okay, you guys see any more? Oh, here's one. Here's one. Do you guys see that one? Okay, any others? I don't think so. Oh, look, there's one peeking its head up over here. Way here. See it there? And I don't see any others. Maybe you can. The next device we want to look at is the transformer. The transformer is the topic of the last lecture, so I don't want to go into a lot of detail here. I'll refer you back to that last lecture. Just remember, we have an iron or steel core with coils on one side and coils on the other. The coils on the incoming side generate an electromagnet in the core The electromagnet in the core generates a current in the core on the outgoing side. The electromagnet is changing because the current on the incoming side is alternating current, or AC, and is switched back and forth from positive to negative. So the magnet is switched back and forth from north to south. The ratios of the incoming voltages and the outgoing voltages is the same as the ratio of the number of coils to the outgoing coils. The purpose of the transformer is to convert voltage. Let's see if we can find any of those. Well, here there's a big one right here. It's got yellow tape on it, so you can't see the cores, but there's one core, they're on top of each other. So they're kind of stacked up on top of each other. So same as this one. Here's the iron cores on the outside, and then the two coils are on top of each other. Again, there's tape on it, so we can't tell that one's smaller than the other. Here's another one with the iron core on the outside, just like the first two. But you can see the two coils in this case, and you can see that they're different numbers of coils on one and the other. So there's 3 transformers on this board. For the next few devices, we have to go back and look at history. Pay attention for now. I'll give you notes later. These are the first radios. This is around the turn of the century, the turn of the 19th to 20th century, about 1902. They're called crystal sets, and they consisted of a crystal of a mineral called galena. Here's the crystal. And what's called a cat's whisker. That's this little wire right here. Here's the handle so you can control the wire. By moving the whisker around on the crystal, the station would come in clear. They didn't know why it worked exactly, but it was they had an inkling that something important was yet to come about here. This is an actual radio set. Here's the crystal over here. Here's the cat's whisker. Here's the handle, so you'd be able to move the cat whisker around on the crystal this way. Let's move forward a few years. A few discoveries were made. One of these being the thermionic effect. If you heat up a metal, down here in the picture, if you heat up this metal, it gives off electrons, which are evaporated off of it. If there's a current running in a wire nearby, here's the current running here. And so notice electrons are kind of just raining down on that wire. The stream of electrons join the current, and the electrons join the stream, and that amplifies the current. Remember, current is the charge per time. So if the charge is increased, so is the current. These devices were enclosed in vacuum tubes, which are tubes with the air sucked out of them. And these are called diodes. It was discovered that if you put a control grid, here's the control grid, here's a thermionic plate over here on the right, and here's the current carrying wire made like a little diamond over on the left. If you add the control grid to it, the devices were called triodes. This led to a variety of different vacuum tubes with a variety of different uses. Here are just a few. The ones that are important to us are number 1, rectifiers, which change AC to DC, and number 4, amplifiers, which increase the strength of a signal. Let's skip forward a few years. It's 1948, and these 3, Shockley, Bardeen and Brattain built the device on the left. This is a transistor. It looks like a mess, but it's the start of something big. These three won the Nobel Prize for that, by the way. The transistor is a replacement for the vacuum tube, and it's a device that takes advantage of quantum mechanics. Transistors are the heart of modern electronics. Transistors are made of semiconductor, and semiconductors are halfway between conductors, in which electrons are free to flow, and insulators, in which electrons are not free to flow. Here's where quantum mechanics enter into it. We will learn more about quantum mechanics on our unit in modern physics. These are just a little of us getting our feet wet here. With materials, there are two bands. There's a valence band, shown in red here, where the electrons are found, and the conduction band, here shown in the bluish color, where the electrons must be in order to move along. With conductors, on the left, the valence band and the conduction band overlap, so the movement of electrons is no problem. With insulators, over on the right, the valence band and the conduction band are far apart, and the electrons can't move. They can't get from the valence band to the conduction band. That gap is just too big for them to jump. But semiconductors, in the center, the gap between the valence band and the conduction band is small enough that we can get the electrons to make the jump. We just have to give them a little push. And there's a couple ways we can do that. Here's how you actually make them. If we take silicon, we can grow the crystal, grow a silicon crystal. Pure silicon has no electrons. But silicon, if we add phosphorus to it, like in this bottom left picture, the phosphorus atoms just take the place of one of the silicon atoms. The crystal is still built. It's just that there's a strange guy in here. It's the phosphorus. And the process of adding phosphorus to the silicon is referred to as doping. You don't want to add too much, you just have to add enough, so every once in a while one of the silicon atoms is taken up by phosphorus. And phosphorus has an extra electron that silicon doesn't have, so now we've got extra electrons. These type of semiconductors are called p-type. P as N for negative because the electron is negative. Okay. If instead of phosphorus I take something like boron, I would get the crystal in the bottom right, where now boron has taken the place of some of the silicon atoms, and I still get a nice crystal, but now boron has one less electron, and so these are called p-type semiconductors, P for positive. Here's a picture of what one of the silicon atoms looks like. You can see they're quite large. Even if this were a small man, that's quite a large crystal that they've built there, they've grown. So it grows quite large, and then they slice it up into these thin wafers. Okay. Here's some notes. They should try and fit them all on the first page of your notes where there's the area for semiconductors. They should all fit in the first place, so write small. So semiconductors, they're between insulators and conductors. The insulators have been forced to conduct. It's a practical application of quantum mechanics. It's made by adding impurities or doping silicon, either N-type, sorry, it should be P-type first, P-type missing electrons or N-type with excess electrons. But the P-type and the N-type alone are not conductors. The key is to combine them in what's called P&N junctions. Heat, light, or potential difference can cause flow, but only in one direction, from the N-type to the P-type. That's the point. If we had a pure silicon crystal, it would with even doped with the phosphorus or the boron alone, where we just built an expensive conductor. The key to these is to marry an N-type with a P-type. That's why you cut them into those thin wafers so you can put them together and get a P and an N-type. And this leads to our first device, made of semiconductor materials, and these are called diodes. Diodes only allow current to flow in one direction, and that has a use. And they are used as rectifiers. They convert AC to DC. And remember those first vacuum tubes, the ones with just the thermionic emission without the control grid, were diodes. So if I put a diode on my circuit, here's our circuit. Here's the battery. Here's a light. There's the diode right there. A current can flow from the positive through the diode, through the light, and back to the negative side of the battery. If, on the other hand, I put it backwards, I don't get any current flow. It doesn't allow current to flow backwards to it. And this current is trying to flow that way, but it can't. It can't because the diode's installed backwards. And 4 of them arranged like this. So if I took 4 of those and arranged them like this diagram in the center, that would give me a AC to DC converter. In other words, it only allows, remember, AC swings back and forth from negative to positive. It doesn't allow the negative to go through. And so we wind up with this, as you see in the top, where all the negative part, remember this is going positive. It should have continued here like that and gone up, and you'd get this nice little wave, but we cut off all the negative part. We only have the positive part, and then we also smush them all together. And you're thinking, well, this isn't quite smooth. You'd want, if it were just 1 voltage, you'd want it to go like that. But as long as it's positive, it's close enough. Let's see if we can find some on our circuit board. And I see one. Do you see one? I see one. I think this is one. Notice there's a little silver on the right. That means the current is flowing only in that direction. And I think there's one there. And the silver is that way, so the current can only flow in that direction through this circuit. And I don't see this one possibly, but again, it's a little small for me to see. Otherwise, that's about it for those on that one. Now there's a special kind of diode called an LED, or light emitting diode. They're all the glowing cat's eyes that you see on your little electronic devices that are still on when you turn off all the lights. And they are diodes. Here's a close-up of one. And by the way, it's got a long leg and a short leg because you always have to hook it up positive in the right direction, otherwise they don't work. So that lets you know the long leg is positive, short leg is negative. The next device we want to look at is a transistor, which is a replacement for the vacuum tube triode. Notice they all have 3 legs. They got an in and out, and then they got an extra one adding electrons to the mix here. And they're made of semiconductor materials. They're used as an amplifier, and they allow current in one circuit to control the current in another circuit. The gate over here is the controller. So normally we just have current flowing through here, but we got this gate which is going to control it. By the way, remember when I told you how important with electronic devices when you're working inside of a computer that you not have an electronic discharge because it destroys the components. This is what's getting destroyed at the gate. The gate here, and once it's gone, that's it. There's no coming back. So a static discharge inside an electronic device destroys these gates. Let's see if we can find any of these. I see some. Do you see them? Oh, there's two down here. There's one there, one there. Notice the three legs. Here's one that's got a real good picture of one right here, and it's got three legs. This one too. Well, what's this big metal thing? Well, that's a heat sink. This must build up a lot of heat, and so they had to put this heat sink sort of like to allow more heat to flow out of it. More surface area, more cooling. So we add more surface area. I suspect that there's one on the other side of this heat sink, but we don't know for sure. See this hole here? See this hole right here? That I'm guessing is the screw is making it touch the heat sink so it can lose heat there. I don't see any. Oh, these two little guys over here. Oh, here's another one of those little guys, and that one is a transistor. Oh, here's one. Any more? You guys got to see any more? Okay. The last electronic device we want to look at, because it's so important, is called the IC, or integrated circuit. And they come in various shapes and sizes. Integrated circuits combine all the other components in one miniature package. This one, the one in the center, is the heart of a computer. Older style, but still powerful. So integrated circuits are also called chips. They can contain billions of transistors and other electronic elements. Up to 9 million transistors per square millimeter is possible. Remember, a millimeter is are the dark marks on the ruler, maybe the thickness of your nail on your big toe. Now imagine that a square, and you get 9 million transistors in that area. And these are made by something called photolithography, which is, or printing or etching. This is the way you print things like books and magazines, and it's built up in layers. So here's what one would look like if we could take the top cover off. This is what they look like, all the little tiny transistors inside and other components, not just transistors. Here's one with wires leading in to connect to all the components. And this one's probably a computer by the looks of it. And let's see if we can find any of these. Well, there's one little one here, back here. And that one definitely is for sure is one on our little circuit board here. And that's our brief introduction to electronics. I hope you got all the notes. If not, you can always go back and pause and get whatever you need. And I'll see you next time.